So that's good. Joaquim, why don't you tell us about the parameters?
So a long time ago, there was an open issue in JuMP about because people were able to use parameters in nonlinear problems, but they couldn't do that for linear things. And there was like a long discussion about that. I think the issue now is closed because I think I started this package. And the idea is, well, most of the time you have a problem, and although you have your variables, you have some things in your problem that you want to change and then resolve the problem. So it's a little part of your problem that you're just changing and you're resolving the problem many times. The first approach to that, okay, just add a fixed variable to your problem and then change that fixed variable to your problem. But then you have to send all that to the solver, and then you have more presolve steps, and that's slightly slower. And if you have to do something like very fast and very efficiently, then you could do something else. Or it's just easier for you to fix some parameters instead of fixing variables. And there is a third application that we'll talk in this presentation, which is about querying duals from those variables or parameters. So in order to show how useful it is, I wanted to actually present some code that uses that, but then I would have to present a Bender's decomposition code, which is like a typical use case for that. And then I would have to come up with a problem that everybody would sort of understand easily. I hope people understand. And so I will try to solve norm 1 regressions with Bender's decomposition. This is not the standard method for norm 1 regressions, but the thing is, norm 1 regressions are just a simple enough problem, so I hope people can understand at least a little bit. And then you can look at the notebook that it's online and understand more and ask me. So first thing first, these are the packages that will go into this presentation. We'll load ParameterJuMP, of course, which is the core of it. We will use JuMP to build our optimization problems. We will use a solver. We'll start with GLPK, and then I will show how to use other solvers, which is basically the same thing because JuMP allows you to change. I'll use this timer output package just to measure the different times of using different kinds of implementations. And these two standard libraries from Julia and Plus. So a little bit of norm 1 regression. Well, the idea is that we have a variable y, and we want to explain this variable y as a linear function of other variables x. And that representation might not be exact, so there is an error in this representation. One way that people, so this is a linear regression model, and we want to estimate these betas, which are the coefficients multiplying the x variables. So one thing to do that is to rely on observations of y and x, which are indexed. So, and then do a linear regression model. So the first thing is that, well, I'm generating some data. So candidates is the number of x variables, and observations is the number of observations that I will have use in my estimation thing. And nodes is something I will talk about later. So this is just building the sinusoids, which will be my functions. And then I will create some random beta coefficients. And then I will create my y variable. So just to simplify everything that I wrote above, just concentrate in this graph. This is representing everything that was above. So I have this blue thing, which is my y variable. It's noisy. I added some noise to that. And this is a linear combination of a bunch of sinusoids with different frequencies. So my problem is I want to figure out which of the sinusoids come into this blue thing with which weight. Okay? And I'm using, I could use standard linear regression with least squares for that, which is this first optimization problem over here. I'm minimizing the difference between all of my observations y and my representation of the function. But what?
You're maximizing.
Oh, Typo. You could maximize, but you won't get anywhere. Pretend that I'm minimizing. And instead of doing the square thing, you could do absolute values, and then absolute values have a nice representation with linear programming. So just because of that. That's not stopping us from using quadratic programming, but just to keep it simple. So this regression thing has this formulation, which is simply formulating absolute values. So we are summing these two variables, and these two variables are both above plus and minus this same thing here, which is in the absolute values. So this will represent the absolute value of this expression, which is the same thing over here, and this is the opposite sign. And both of these are positive. So this is just representing the absolute values. And what do I have in this problem? I have all these constraints for all the observations. So I build one constraint for each of the observations. And my variables are just betas. So I have one variable for each of the betas, which are my candidates, sinusoids, for representing my original sino or something like that. So it won't fit the screen, but you can bring that problem that I wrote in LaTeX to JuMP. So this is a little bit of propaganda, just saying that, well, you can write almost the exact same thing that I wrote in LaTeX in JuMP with even like nice syntax like sums and belonging. And well, I was asking Stefan the other day if I could use for all over here. There's an open issue in Julie about that, but it would be pretty awesome, wouldn't it? So yeah, this is representing the full problem. So I added all my observations and all my candidates, and I added my objective function over here. And then I will solve this problem with GLPK. And okay, the problem is solved. I have an objective function, and I have the time it took to solve and to build the problem. So it took like 0.6 seconds to build the problem. This is just a small instance. We can go bigger later. But the big thing over here is, well, a little bit of Bender's decomposition. We heard Bender's words many times in this workshop. Even when people talk about SDDP, there's Bender's decomposition inside there. So this is the kind of problem that we're solving with Bender's decomposition. I took this from Bertelsman's book. Well, we saw that structure, I think, with Invitor's presentation. We have this same variable over here and many blocks. So the idea is to decompose the problem in two parts. The first part will be everything relating to the variable x, and the other blocks, the variables y. So the idea of how to do it, yes. So I create this. I will first create the subproblems, which are also named slave problems, which will be like just problems with the y variables. So this block will be one problem by itself that is represented in this way. This x will come as an input to the subproblem, so it's moved to the right-hand side. So x will be a fixed variable over here. This is what norm one regression will, the subproblem of a norm one regression would look like. So how I partitioned that, I just created this observation set. So each of my subproblems now, actually the norm one regression is fully decomposable. You can do like one subproblem for each variable, and it would be like a stupid subproblem just asking whether those epsilons are larger than something. But you can take like a subset of the observations. So like, say I have 1,000 observations, and I want to create 100 of these subproblems. Each one will have 10 observations. So it's like I'm estimating the error of 10 of them at the same time. It's kind of not the smartest thing you should do, but it's easy enough to explain what I want. So I create the function for the observation set, and then I write my slave problem. Again, I will be doing writing exactly the same thing I wrote in LaTeX. The only difference here is that when I create my beta variables, which are what I'm explaining, I have two options. Either I create the beta variables with parameters, or I create the beta variables with variables fixed at some numbers. Okay, I will start at 0. And then I write the constraints. These are just some extra. Okay, this is the master problem. We'll talk more about benders later. So again, the master problem is just like the LaTeX form. This is a general master problem for our problem. Nodes will be like the blocks of variables that we're solving. This is the master problem. Currently, it's super easy. But then we will add constraints to the master problem, which is part of what Bender's decomposition is doing. So, okay. So what I wrote this other function, which is slave solve, which what is doing? It gets some data, so betas, it gets betas. It sets the values of the betas of our master problem, of our subproblems, to the values of betas that the master problem decided. So it's fixing in 2 different ways. It's either fixing with JuMP parameters or fixing the variables themselves. And then I can query the duals for, well, either from the parameters or from the variables themselves. And then I create a Bender's cut, which depends on the dual variables and the objective of the slave problem. Then I created this small function to add a cut to the master problem. So I grab all the data that I obtained from solving the subproblems, and I add this constraint over here to the master problem, which is, well, the dual variables multiplying the variables of the master problem. So algorithm wrap up, we solve the master problem, obtain a solution, and then we fix the values at the slave problems, solve the slave problems, query the solutions to obtain supporting hyperplanes, which are defined by dual variables and constants and objective values. We add the hyperplane to the master problem, and we repeat. So this was implemented here in decomposed model. And this is, well, basically the implementation, it's very verbose. So Julia has many more lines than LaTeX just because I added a bunch of comments and some timing things. So the thing I wanted to show is, okay, now if the first version will solve with the constant parameter equals false, which means it's solving with standard JuMP, fixing the values of the variables. And the time it takes to solve, it's like, it's down here, 1.2 seconds, which is double of solving the full problem. But this is a very small problem. But if we solve with parameters instead of fixing the variables, we are back in the same time as solving the full problem. But then you can solve a larger problem. Now I'm solving, before it was like 100 and 600 and 100, I think. So now it's a much larger problem. And when we solve with the full model, it takes like 8 seconds over here, time to solve. And then we solve with each of the decompositions. With JuMP itself, fixing the variables, it takes 12 seconds because the problem is that the slave problems will have much more variables than they actually need to have. So solving the problem is much harder. And solving with the decomposition with parameters, it takes only 4 seconds, which is half of the solving the full problem. And this is a medium-sized problem. And what I did last was now a much bigger problem, now with 700 candidates and 5,000 observations. So I solved the full model. It took like 268 seconds on Express now because GLPK was not solving this problem very well. And then 268, keep the number in mind. And then you try to do the decomposition. When you don't use the parameters, you use regular JuMP variables. You got some improvement now. It's 100 seconds faster than the full model, now that the composition is helping us. And with parameters, it's taking 90 seconds, which is 1/3 of the full problem and half of the adding the variables themselves. So yeah, that's what I wanted to show you. It's like the performance gains of doing this sort of presolve made by using those parameters instead of fixing variables and adding them to the solvers without need. That's it.
So maybe one question while we get set up for this.
Should be on the flash drive.
On this one?
Yeah.
You can only fix the parameters.
Which one is it?
The problem with
That one.
variables is that the variable will still be there, so you're not helping the solver. So you can use plain JuMP syntax to change the coefficient. Using parameters won't help doing that fast, and you won't be able to query duals from that also. So those two things are not helping. But maybe